Hello and welcome back to the AI Masterclass. In this tutorial, we are talking about the mixture density networks. Hope you're as excited as I am. Let's dive straight into it. So here we're going to assume that we have a classic neural network. We've got an input layer with some neurons, then we've got a hidden layer or multiple hidden layers, and then we've got an output layer where we're predicting one value. And to give this problem a face, let's look at a specific example. Let's say we have lots of images of dogs and puppies, and we want to predict or determine their weight, establish their weight based on the image. We want to train the neural network to do that. It's a supervised problem because the inputs actually have the weights attached to them. So what we're going to do is we're going to pass this image through the neural network. We're not going to go into details about how this image is processed. That's the job of a convolutional neural network. We'll assume that there's a convolutional neural network in here. In fact, this could be a completely different problem. It could be just like a vector of values that's going into the neural network, and therefore the convolutional neural network isn't required. Basically, we don't really mind what's going on here. That's not our focus. We're just looking at these images of dogs so that we have something more visual to talk about. And so the values are passed through the neural network, and then the neural network outputs a prediction or a value that it thinks that's the weight of the dog is 4.3 pounds. Actually, the weight of the dog is 8.2 pounds because we know the weight. This is supervised training. And so what happens then? Backpropagation goes back to the neural network, and the weights are adjusted so that next time the prediction is going to be more accurate, and so on. And so happens the training. So we've got more images of dogs going through this neural network, and it gets better and better at predicting their weights. And so once the training is done, what we'll be able to do then is we'll be able to take a picture of a dog. Let's assume like we have this dog here and we don't know the weight of the dog. We'll be able to put it through a neural network and get a weight, and we will have a value that we can say that this is the weight of the dog. This is what the neural network says, that's the weight. Now, this is a classic neural network or deep learning problem. What we're going to do now is we're going to change it up a little bit. Let's say that instead of outputting a deterministic value, for instance 5.5 pounds, we want our neural network to give us a range, to give us more precisely, to give us a distribution of values, of possible weights of this dog. So it would look something like this. So instead of telling us that the weight is 5.5, it would tell us that the weight is somewhere around 5.5. So the mean of this distribution is 5.5 pounds, and the standard deviation is 0.4 pounds. So basically we want the neural network to give us these two values and tell us that the weight of the dog is somewhere in this vicinity. The closer you are to 5.5 pounds, the more likely it's here. The further away, the less likely. And let's have a look at some examples of how this could be useful to us. Why would we want that to be the output rather than a deterministic value? Well, because if we do that, then if we put this mean value here and go one standard deviation to the right, one standard deviation to the left, then we, based on how distributions work, we can say with a 68% confidence that the weight of this dog is between 5.1 and 5.9 pounds. And then if we go even further and take two standard deviations each way, then we can say that with a 95% degree confidence that the weight of this dog is between 4.7 and 6.3 pounds. So in some business problems, you might want a deterministic value. In others, you might want a distribution, and then you'll do certain things with it. Like in this example, we looked at different standard deviation ranges. In different business problems, in different other problems, you might have different use cases for having this, or reasons for having this distribution. So the question is, how do we get our neural network to output a distribution? Well, one value is not enough. All we need is actually two. We need the mean of the distribution and the standard deviation. So that's what we're going to ask our neural network to output. And through the same process or a similar process of training, it will learn how to output not just the one deterministic value, but the two values which describe a distribution for that given dog. So for any given dog, it will be able to output these two values, and then we will use them to find the weight that we're looking for. So that's how we can get a neural network to output a distribution. But that's not all. Here, as we can see, we assume that this distribution is a normal distribution. What if the distribution is not a normal distribution? What if it's a general type of distribution? For instance, something like this. Well, what we're going to use in mixture density networks is an assumption that any general distribution can actually be broken down into a mixture of Gaussian or a mixture of normal distributions. So in this case, it looks something like this. So as you can see, we've got two Gaussian distributions, the red one and the blue one, and together, combined, they create this purple distribution, which is a more general type of distribution. And so based on that assumption, we now can upgrade our neural network to look something like this. So we have our input layer, our hidden layers, and then as the output, we don't have just one pair of values, the mean and the standard deviation. We have multiple pairs of values for every single distribution. So if we have two distributions that are approximating our general distribution, if we were going to limit ourselves to two distributions, then it's that. We could actually have more distributions. We could have 5, 10, we could have 100 distributions. That's totally up to us. Now, right away, the first thing that pops to mind here is the question about alphas. What are these alphas doing here? What are these values? We don't just have pairs of values, the mean and the standard deviation. Now we have 3 values for every single distribution. Well, the alphas are very essential for this whole mixture density network setup. They are the weights at which these distributions are added up together to get to the general distribution. So if we look at the next slide here, our mixture model is the sum of alpha 1 times the first distribution plus alpha 2 times the second distribution. And plus, we could have, once again, we could have many more distributions, and each one of them would have its own weight. A quick note here is that the sum of these alphas has to be equal to 1, and of course the neural network could output, doesn't have to follow this criteria, but the way we do get it to follow this criteria is we use the softmax function to make that happen. We're not going to go into detail on the softmax here, but just in case you're wondering, that's how this is accomplished. So there we go, that's how a mixture model works, and as a result, what we get is the input, in this case, our image of a puppy, can be translated into a mixture distribution, which will describe, well, in this case, the weight of the puppy, but in a business problem, it can be just a mixture distribution, so a general distribution broken down into Gaussian distributions that is telling us where our answer is likely to be, and then we can use this to feed further into other interpretation mechanisms that we might have in plan for this specific business problem. So there we go, that's how mixture density networks work. We've got some additional reading prepared, or suggestions prepared for you guys today. The first one is Mixture Density Networks by Christopher M. Bishop, 1994. That's where they originated from. It's quite a big paper. Have a look if you'd like to dive deeper into this topic from a theoretical standpoint. And actually, this time we're going to have 2 additional readings, because if, on the other hand, you want to dive into this from a practical standpoint, there's a very interesting paper from 2018, quite recent, called The Probabilistic Forecasting of Household Electrical Load Using Artificial Neural Networks. Very interesting paper, and here they compare using a mixture model to other approaches in artificial neural networks for predicting household electrical loads. Quite an interesting business or industrial application for neural networks. So in this example, we looked at puppies. Here's an actual business problem if you'd like to see neural networks and mixture density networks in action. On that note, thank you so much for being here. I look forward to seeing you back in the course in the next tutorial, and until then, happy analyzing.